Hello, National 5 chemists. I hope you're all doing really well and ready for some more Unit 3. Today we're going to have a look at redox. Now, a redox reaction in chemistry is comprised of both a reduction and an oxidation reaction. So in order for us to understand what redox is, we're going to have to understand first of all what reduction means and what oxidation means. So reduction then, well, reduction is the gain of electrons. So if in a chemical reaction something is gaining electrons, it is being reduced, or it's a reduction reaction. Now that might seem back to front to you. You might be thinking initially, if you're reducing something, if something's a reduction reaction, surely it would be losing, not gaining. But unfortunately, that is the case in chemistry here. What we're talking about, reduction reactions, are the gain of electrons. And therefore, what's an oxidation reaction? Well, it's the opposite of that. Oxidation reactions, that is the loss of electrons. So we've got two different types of reactions here. A reduction reaction, which is the gain of electrons, and an oxidation reaction, which is the loss of electrons. And together, they form redox reactions. And that's where the name comes from. Red comes from reduction, oxidation. And it makes sense that they would occur together, because if something is to gain electrons, it's going to have to gain them from somewhere. So something else has to lose the electrons. So they occur in tandem and parallel with each other. Wherever you get oxidation, you get reduction, and vice versa. Now that can be a little bit confusing to learn, right? In terms of reduction is gain and oxidation is loss. Nice way to remember it is if we remember the word oil rig, one of these things that you find out in the North Sea to drill for oil. Oil rig is a nice little way that we can remember the correct definitions of these reactions. So O is oxidation, I is loss. So oil rig, the first part, oil, oxidation is the loss of electrons, where reduction, the rig part, well, that is the gain of electrons. Now, if we remember oil rig, we should remember these two reactions. And as I've said, these two reactions always occur together. If you have an oxidation reaction, you also have a reduction reaction. Now, you are all very familiar with the data booklet, and you've probably, when you're leafing through it, have seen this page before. It's the very last page, page number 10, and we have this, I suppose it's like a league table of different metals, with our most reactive metals at the top and our least reactive metals at the bottom. This is called the electrochemical series, and within the table we have got all of these little reactions, sometimes called half reactions, and they are all an example of reduction reactions. Every single one of these reactions is a reduction. Remember to what we said earlier, oil rig, oxidation is loss, reduction is gain. So all of these chemicals are gaining electrons. And let's just check that. I've got lithium positive ion plus an electron, gaining an electron, becoming the lithium atom. Next one, potassium positive ion, gaining an electron, becoming the potassium atom. So these are all reduction reactions, and they're all gaining electrons. If I'm ever asked to write down a reduction reaction in my National 5 chemistry test or exam, I should go to this page and just copy down exactly what is said. So if you were asked, for instance, to write down the reduction reaction for sodium, I would go to this page, page 10 of the data booklet, go down to sodium and write down Na positive plus an electron. It's a reduction reaction, so it's going to be gaining electrons, turns into Na, the atom. And it's as simple as that if I need to write down a reduction. For an oxidation though, if I was asked to write an oxidation reaction instead of a reduction reaction, well, I don't have a page in the data booklet for the oxidation reactions. They're only reductions here. So to write an oxidation this time, instead, what I would have to do is to find the element I'm looking for and write the equation in reverse, flip it round. So I'll show you an example of that. Let's say I was asked to write down the oxidation for, I don't know, let's go for aluminium. I wanted to write down the oxidation reaction for aluminium. I would go down, find aluminium. I can't write it exactly as it is here because that would be the reduction reaction. So in order to write the oxidation reaction, I just write the equation in reverse. So I start with the product and write that on my reactant side, so Al, and then I put my arrow and I write this part, Al3 plus 3 electrons, and now I've written the oxidation reaction for aluminium. So it's that easy. Reduction reaction, you just write it exactly as it is. For an oxidation reaction, we just reverse or flip the equation. And I can always double check to see if I've done it right if I remember oil rig. I was asked to write down an oxidation for aluminium, so oxidation is the loss of electrons. Let's check it out. I've got aluminium as my reactant, turning into the Al3 plus ion by losing 3 electrons. So that aluminium has broken down into Al3 plus, and it has also lost 3 electrons to do so. Okay, I've done it right. And the same with the reductions. Reduction should be gaining the electrons. Now, sometimes we can be asked not just to write these half equations that we've looked at here, but also we can be asked to write a full redox equation. And that involves us combining together both of the half equations, combining together the oxidation equation and the reduction equation to write the overall redox equation. Now this is it's quite straightforward. When we look at a couple of examples, you'll see exactly how straightforward it is. The only thing that you have to remember when writing redox equations, when combining these half equations, is that the electrons must be balanced in order to combine them. If they're not balanced, if we've got 2 electrons in the oxidation half equation and 1 electron in the reduction half equation, I can't put them together. They need to have the same number of electrons in order to balance them. So we'll look at doing a couple of examples now and you'll see exactly how easy it is. So here we've got an example. They're asking us to write the overall redox equation from these 2 half equations. We've got the magnesium atom breaking down to form the magnesium 2 plus ion by losing 2 electrons. So there's our oxidation step. And underneath we've got the silver 1 plus ion gaining an electron to form the silver atom. So here's a reduction step and we need to write the overall redox. Now, as I said before, what we're wanting to do is to combine these 2 equations, but in order to do that, we must have the same amount of electrons in each equation. So, in the top equation, in the oxidation step, I've got 2 electrons. In the bottom equation, I've only got 1 electron, so they're not balanced. In order to balance them, I would just simply times through that entire bottom reduction equation through by 2, everything times by 2, not just the electrons, but everything. And now I can start to put together these 2 equations to write my redox equation, because they now have the same number of electrons. So to write the redox, all I do is I take everything on the left hand side of my 2 equations and write them out into one line. So I've got magnesium plus 2 Ag1 pluses, don't forget the charges, plus 2 electrons is turning into Mg2 plus 2 Ag, and 2 electrons. Now, we're not done just yet. This isn't the final redox equation, because in a chemical equation, like a redox equation, we're not allowed to have any electrons present in that completed redox equation. They need to be cancelled out. And it's a little bit like, I suppose, maybe simultaneous equations that you do in maths. I've got the same things on both sides. I've got these 2 electrons present on both sides of the equation. They can be cancelled out. And the final redox is Mg plus 2 Ag positive, giving me Mg 2 plus 2 Ag. There's my final redox equation that does not contain and must not contain the electrons. So what did we do? Well, we simply balanced the 2 half equations, we wrote them out into one line, and then we cancelled out the electrons. Dead straightforward. Okay, same idea here with a slightly different question. It's asking us to write the redox equation. We've been given our 2 half equations, the oxidation step for sulfite ions and the reduction step for these iron 3 plus ions. To write the overall redox, we need to make sure, first of all, that we have the same numbers of electrons in both equations. Oxidation step has 2 electrons, reduction step so far only has 1 electron. So to balance those out, I need to put a 2 in front of everything in the reduction step times the whole reduction step through by 2, and I now have the same numbers of electrons. At this stage, once I've got the same number of electrons, I can write everything out in one line to start to get together my redox equation. So I've got water plus these sulfite ions, and that's everything on the left hand side, so I'll stop now when I get to the arrow and go to the reduction step, plus these 2 Fe3 plus ions plus 2 negative electrons is turning into our sulfate ions plus 2 H plus ions plus 2 Fe2 plus 2 negative electrons. So I've written out now everything in both of those equations into one line. Not finished because, as we've said, the redox equation cannot contain these electrons. So that's why we do this first balancing step. It's in order for us to cancel them out in this step here. I've got the same things, exact same things on both sides of my equations, 2 electrons on both sides. I can cancel them out and write down the final redox calculation, which does not include the electrons, just includes the balanced chemicals and elements. And here is our final redox equation. Handwriting is poor as usual. I apologise. These should be F's, of course. And that definitely is not correct. That should be 3 plus. This is the Fe3 plus ion, not the 2 plus. 2 plus is on the right hand side, 3 plus on the left hand side. So you can see there, while this is quite straightforward to do, it is very easy as well to make daft little mistakes, especially if you forget to put in the charges on the ions, or if you left in these electrons. That's the only time that you could probably drop marks here. So I hope you found that video useful, and I look forward to seeing you all again real soon.